Now, it turns out everything we're doing relates to everything we've done. How cute, right? So delta G naught and equilibrium have a relationship. Kind of, on the side. I don't talk about it a lot, but they're pretty good friends. You know what I'm saying? So here we go. The phrase, which they've been using a lot, I use spontaneous, whatever. The thermodynamically favored, where G is negative, right? Means that the products are favored at equilibrium. Because what we mean here, if it's thermodynamically favored, meaning if it happens, that means I'm making A, B, and A and B are going down, right? So I'm making more products and the reactants are going down. You with me? All right. So then that would mean K would be greater than 1. Right? That because product's big, reactant's small. That's how you get a value that's above 1. At equilibrium, no net change in concentration of reactants and products occurs because we're making the same amount. So free energy at equilibrium constants have the following relationship, or sorry, and the equilibrium one. All right, this is the most common way, you'll see it, but they are the same. It's the same equation, just one you're solving for K, and the other one you're solving for delta G naught. And you see E raised to negative delta G over RT. E is the inverse of ln. That's why they are there. Now, this R, it is the same R from gas laws, but it's a different unit to make things work. So it has a different number. And that's kind of weird. If you think way, way back, I showed you a slide that had 5 different values of R, but it's just because they had 5 different units to make the math work. This is piv nert, but it's a different value because it's a different number. Memorize it quick. For these, R is equal to 8 pi. 8 pi. 8.314. Yeah.
Will it be giving us the values of R?
Yeah, that's right on the reference sheet. And you're never going to use like the point or like the 64.35 or something like that. Like I've never used that in my entire career. I've only used this one, 8 pi as I call it, and 0.0821. What's that? Yeah, E, I don't know what it is, but it's the button on your calculator. Right. Not a variable. You're right. Okay. Now you don't have to have these memorized because they are both on your reference sheet as well. But you do have to know how to use them. Okay. Like a million things. You'll see one. No, to memorize. Yes, in the review, you'll see how it works. It's really nice too because they're grouped by like what you would use them for. So like these would be written in the thermodynamics section. And you're like, oh, I'm doing a thermodynamics problem. I probably need this area. All right. There's way, way, way more of them though. I thought you said you already did it. Oh, well, I don't know when they're for, but they're okay. So far, here we go. Connections between K and delta G can be made qualitatively through estimation and quantitatively, but we can just look and think, all right, well, what would this do? When delta G is negative, K is greater than 1. All right, because if you take the ln of a negative number, it's a positive and then that blows it up. All right, or vice versa. When delta G is positive, K is less than 1, and the reaction favors the reactant. Okay, this is tested often. This is a pretty quick multiple choice question. And honestly, this is almost always the answer. If you do it and it's like 0, you're like, what does that mean? Oh, that means it's at equilibrium. Probably, but I wouldn't stress too much about it. Like whenever anyone tries to get me down on a specific answer and you use the word ever, I always say no, because chemistry is a book or science of exceptions. All right. Do you have that either pictured or written? Yes. There you go. Yeah, they're like the law of conservation of matter, things like that. Except for when we don't. Okay, are we all right with that so far? This is just math, and I'm not a great mathematician, but when in doubt, just plug in a positive or a negative number and see what it does in your calculator. When in doubt, make crap up and see what happens. What does a negative G mean? Like ignore this. What does a negative G mean overall? All right, it's going to go towards the products. It's thermodynamically favored or spontaneous, all the above. Okay, here we go. So this is a free response example. Use principles of thermodynamics to answer the following questions. The gas N2O4 decomposes to form the gas NO2 according to the equation below. Predict the sign of delta H for the reaction and justify your answer. B, or double I, or 2, whatever, predict the sign of delta S for the reaction. Justify your answer. Okay. Do you want time or do you want me to tell you? Time? All right. That's good. I don't mind a little break. All right. So here we go. First off, what do you think? Positive or negative? Positive. Why? Sorry, Tim. No. No. Sort of. This isn't releasing heat though, but it's separating. I heard it. Someone. Oh my gosh. Text your dad. Text your dad. It did. Weird. Well, this isn't from this chapter. He absorbed it in chapter 8. Bond breaking always requires energy. Bond breaking always requires energy. Yep, like we'd have to heat it or something like that. Okay. So, yep. Now, number 2, what do you think about this one? Is entropy increasing or decreasing? Increasing. And this is how we know why. We've gone from 1 mole of gas to 2 moles of gas. Or we've gone from 1 independent substance to 2. Chaos or disorder is increasing. All right, on the diagrams below, one of the diagrams below best represents the relationship between delta G and temperature for the reaction given in part A. Assume that delta H and S are independent of the temperature. Okay, how do we do this? All right, we have this equation, right? So let's put them in. Delta G equals a positive value, right? So I'm just gonna put 5. Sounds good. Minus the temperature. You all right with that? Times what sign here? Positive. So as this number gets bigger, the number I subtract is getting bigger, right? So it decreases. So which one am I circling? Kind of, Seth? Okay. kind of everyone else. So you just kind of think, and I mean, we could have just left this as whatever we felt like, an H or whatever. But you got to think about what the sign is doing. If it ever talks about temperature here, it's really asking you, what's the sign of S and how does that affect it? Okay. Let's see what we got here. Okay, so this is just this is like C and D of the same problem. A reaction mixture of that is at equilibrium. Heat is added to the mixture while it is maintaining the constant pressure. Explain why the concentration of N2O4 decreases. The value of that is that, and try those for a couple minutes. Did I record? I did not. Oh, I did. Okay, take a couple minutes and try these. There's some math this time, isn't there? I think we're fine. What am I doing? No. What am I doing? That's what I'm doing. Oh, hold on. I still need to rearrange these because that one should go there and we should be here. What? Okay, so here we go. This is the answer up here. I think it's all, no, yeah, it's broken up. Okay, the reaction is endothermic. So if we add heat, we're going to make more products, right? Is everyone okay with that? All right, you can use Le Chatelier's principle here, but I don't know, it is Le Chatelier's principle, but I would make sure to use the words endothermic. Okay, by adding more heat to an endothermic reaction, you will produce more products. Because we said it was. Because a long time ago, we said it was endothermic. So more heat makes this go down and these go up. Yeah, sorry, that could be confusing if you didn't. All right. So there's that answer. Because the reaction is endothermic, at higher temperatures, the reaction goes further to the right. You with me?
You have to explain it.
It makes more products. I don't think this one did. No, you don't have to. So, yep, you just need that. This means the KEQ at 100 will be greater. Yep. So the key here, endothermic. When we said, hey, I think most of us were okay here, like we added heat and it made more products. Okay, well, we may not realize it, but what we're doing here is we're going at 25 to 100. So we're adding more heat. So we're making more products, which is the numerator, the denominator smaller, so K has to increase. Okay, it was really the same question, just very veiled and harder to tell. All right. K at 25 is less than 1. Hence, delta G must be positive. Good luck. What's your passion? Let's see. Okay, just not around me. There's some essential oil that like makes me throw up. I don't know which one it is. Okay, you're good. Yep.
This is the answer.
This is the answer
Of part D.
of part D.
Which we didn't do.
Oh, was D not on there?
I know. Oh, it was. We just didn't do it.
Okay, you haven't read it yet. You didn't really read the answer anyway. So look at letter D.
No.
No. Same hair too.
I love it.
Okay, are we ready for the answer? Oh, I'm waiting. I'm gonna wait. What? The second one on C was the same. Like since we added heat, it made K bigger because we made more products on top in the reaction, like the equilibrium expression. The products were greater now than the reactants, so it got higher. All right. So look right here. I got to go back to C for a second. See how it's a decimal point 0.005? Okay, so it's less than 1. That's where it's getting this data right here. Since it's less than 1, what does less than 1 mean? Reactants are favored, right? All right, hence delta G must be positive, meaning it wasn't favored. The reverse was favored. That's why K was a small number. And delta G, and for delta G to be positive, delta H must be greater than T delta S. This is a very tricky question right here. All right, it makes you think about a ton of different parts here, because we're really looking at delta G naught, and it's equal to delta H minus T delta S, correct? But we're also really relating it through K, right? So we knew K was 0.005, which meant it was less than 1. And that means that G has to be positive from this slide a year ago already. Remember this? Like it's tying so many things together. Okay, where was I? Right here. So, and for G to be positive, this has to be overly, like it has to be a positive value, right? This piece has to be bigger than this piece, because this was a negative. No, was it negative? They're both positive. Wait a minute. See, I just blew my own mind for a second. Oh, I just read it. I wrote bigger in the wrong spot. Sorry. Thank you. Call me out earlier so I don't have a heart attack. All right. For this to be positive, okay, finally, sorry. This number has to be bigger than this number. So like how many different levels of things do we have to connect there? 4. Like that's a hard question. But the good news is if you got all the other ones right, you're going to get a 5 on it. Like every one of the free response usually has one that is just a butt kicker. But it's okay. Most of them are worth 9 points, 7 or 9 points. And if you can get above 50% on them, you'll do fine. All right, summary. Thermodynamically favored means the products are favored at equilibrium, or K is greater than 1. The equilibrium constant is related in these examples. I think I have a math practice one coming up. Connections can be made qualitatively through estimation. That's what we did a couple of those. We didn't do really any math. We did thinking about the math. All right, I better have one. Hold on. Okay, here we go. All right, this is my typing. So it's not like a perfectly written one from the AP test, but we can figure this out. We have the Haber process, because why wouldn't our book have the Haber process in it, right? We're going to make those assumptions. You have A, B, C, and D. I don't think I can make it all fit on the same screen and have people read it in the back. Let me see what I can get here. Oh, can you read it in the back row? All right. So take a few minutes. It's up there in difficulty. So here we go. Predict the direction of delta G for this reaction with increasing temperature. Explain. So remember, delta G equals delta H minus T delta S, correct? All right, H is a negative 92.38 minus, all right, what is delta S? A positive or a negative? Negative. So this is really going to be a what sign? An addition. So we're going to have negative 92.38 plus whatever. If this is a small number, or this is a big number, it's going to change things, right? So as does it say as temperature increases, right? As the temperature increases, we're adding a bigger number. So predict the direction in which delta G, you would say it becomes more positive. That's all you got to write for that part. And to justify, you would say because the sign of entropy is a negative value, which means the T delta S is a negative, which means you add all that fun with signs. You got that part right. Okay, and the justification pretty much the same. Okay, so it's all about what this term, it's about what that multiplied turns out to be. And since it was negative, we really add, which means it gets more positive. Okay, then we're going to calculate these values for G naught at 25 degrees Celsius, which is not 25 degrees. It is 298 and 773. Now look, if you're Delaney and you're mad at yourself, it's okay. Like you can be mad that you forgot to do that, but if you did the process right, I'm okay with that. Just remember now, you got to put it in Kelvin because this unit is in Kelvin. Okay. And you're in chemistry class. What's our temperature? Kelvin. We've been doing it all year long. Okay. So delta G is equal to, what do you want? Do you want it in kilojoules or joules? Kilojoules. So I'm going to say that this then is negative 0.1984 kilojoules. Are you okay with that? Okay. So I would do that at the start, by the way, if I were you. So delta H is negative 92.38 minus, what are we at here? No, 298. And S was I'll go X, 0.1984. Negative, thank you. No? What did I do wrong? It's negative. Okay. Now, help me out here. I don't want to type it in, but there's probably 8 different answers here. What do we get? Negative 33.25. Does anyone agree with that? That felt good, right? Okay. That's it for that. Yeah. They just have to match. That's all that matters. They need to be both the same. Now, that answer is in what unit? What did I choose? Kilojoules. Okay with that? All right. Then we do everything the same right here. Negative 92.38 minus 773 this time is your only change times negative 0.1984. And that equals all right, 60.98 kilojoules. Do we agree with that? All right. Was this a negative? Was this a positive? Okay. All right. So now explain why a producer of ammonia would want to carry this reaction at cooler temperature. Okay, that's all great and all that, but we have to like talk about these numbers. No, this is not endo or exo. This is G. At lower temperatures, it is thermodynamically favored. Products are favored, that is right. But please make sure you include, like we did this math for some reason, we did that explanation for some reason, they're gonna tie to letter D. So make sure your answer includes the fact that at lower temperatures, we had a negative sign. It's spontaneous. At positive or higher temperatures, it was non-spontaneous. But there was one little note yesterday that said something important. It said at spontaneous, it doesn't mean it is fast. And we learned this problem before. We learned in rate laws that they really do it at high temperature and high pressure because the reaction is really slow. Even though it is thermodynamically favored, it takes too long to be something you can make money out of. Okay, and I think that it's not on there, but letter E used to say, in reality, they do it at high pressure and temperature. Why would they do that? And it's about the rate. All right. How would it be to be as cool as Jared Torrey? Okay, I feel the same way. When are we out of here? 1 minute, 5 minutes, 10 minutes? 5 minutes. Might not have time to do this completely. Why don't you look at it and try to do it tonight? And we'll start class. I think this is the last slide. Okay. No, oh crap. I forgot we still have coupled reactions. We'll be all right. I wanted to take 3 days. We're gonna take 3.5.